Hello everyone. Can you all hear me? Awesome. Is my voice is loud and clear, I guess. Good, good. Great. So we are at a very critical juncture, I think, right? What we are now deep into neural networks. Have you guys done any lesson and projects on your own? Are you guys able to finish it? Did you guys find time to at least go through some of them? And if you haven't, I think I strongly suggest on this Saturday, Sunday, over the weekends, you might actually, you know, want to invest some time over it, right? Um, Good, good. Uh, shall we start with a small quiz? I just wanted to, this is our fifth day, and maybe it's good for us to actually, go through some of the questions, some of the things that we have done. Okay, this is impromptu, nothing serious about it. Any of you can answer. Um, can any one of you tell what is the first layer of a typical neural network? What is the first layer of typical neural network called? It's called as an input layer, correct, right? And what is the last layer of a neural network called? Output layer. Okay. And what are the intermediate layers are called? How many such intermediate layer can be possible? Yeah, hidden layers. How many such intermediate layers can be possible? Question is how many such intermediate layers? It can be any. Perfect answer. Right. As many as needed. There is no hard and fast rule. Okay. Correct. In a typical classification problem, what will be the last layer's activation function be? Right. I think softmax is the right answer. And the second question is, yeah, so how many number of neurons on the last layer will be equals to your number of classes that you have essentially, right? Awesome and good, good. Right now, so say I have a I have a data set and which has 1,000 samples with 10 features. Okay, it's 1,000 samples with 10 features. What will be my first layer, first hidden layers? Weight matrix will look like how many such how what will be the weight matrix will look like if I have 1,000 into number of neurons. Perfect, right? Yeah, that's a yeah. So number of neurons is on you, right? You can decide how many number of neurons you want. At its lowest level, what are the two fundamental operation a neuron does, an artificial neuron does? Summarization and an activation operation. And what is an activation operation? Yeah, I mean, sigmoid is a type of an activation operation, but what is it? What does an activation function do? Tanh is also correct. So what is the role of an activation function? Why do we need an activation function? An activation function does not gives you probability. By the way, the activation function does not gives you probability. An activation function is an output of weight matrix multiplication. It is not what it is. But Pawan has said the right answer. It provides non-linearity in the system. If you don't have an activation function, what will happen? Suppose you have created a dense layer where you have not added an activation function of ReLU, okay, or tan H or sigma. What will happen? What do you think will happen? If you don't add non-linearity to the system, what will happen? Ultimately the network will become, linear, right? It will fall down to a linear model itself, isn't it? It's gonna be a large linear regression or logistic regression kind of thing, right? What are the two fundamentals? So promise of neural network is what? That it works for any data set, right? That is what the promise is. What are the linear? Okay, what are the hidden layers? So we have gone through this hidden layers. Okay, what is the key differentiator that a neural network versus a classical machine learning techniques bring? If you have to pinpoint to one, there are many, but if you have to pinpoint to one, which one will you pick? The key differentiator between those two techniques. Yeah, features get not inbuilt, the extraction happens in the hidden layers. So the feature extraction happens in the hidden layer, right? So let's be very clear on that, right? And how the feature extraction happens, how are we doing it? If you don't add, so if you remember, right, if you add the activation function, if you add non-linearity, that's where you can get higher order features, right? So that is what it is. What else did we go through here? What else have we gone through? What is the forward pass? How do you define a forward pass of a neural network? And okay, from hidden, so you right, from hidden to from input to hidden to output. And how do you go to output is fine, and then there's something else is also there. Now after output, what happens? You have an output, and then there's something else happens. Yeah, you have to add the loss function computation, right? And then what happens after this? Yes, correct. That is important, right? So without the loss, so forward pass is one full of that. And then after that, what do you mean? What happens after that? We need to do a backward propagation. And why do we need to do a backward propagation? Try to find out, recalculate. So okay, what does the backward propagation do? It doesn't adjust the weights. So it can recalculate the change in weight. Perfect. Who adjusts the weights? Which algorithm adjusts the weight? It's generally also gradient descent. It's gradient descent and some flavor of gradient descent. And I think we will look into that today. But essentially, they are also called as, what are they called as generically in a typical neural network? They are called as, this class of algorithms which actually apply the updated weights is called as optimizers. Yeah, optimizers, right? Right. So they are extremely key. They are the one who actually applies the rate, right? So it is not good enough to know that how much you have to do. You have to really traverse the path, right? The traversing the path, that is then applying the weight happens in a optimizers. Yeah, you have already told GD, which is gradient descent. Can you name one more optimizer that we probably have used in our, you have used SGT? Yeah, definitely. Adam also is and yeah, Nadam also is there. Yeah. Okay. Great. So, and how do we compute? What is the core proposition of backward propagation? How does it compute the backward what happens? How do you know that loss to weight? Chain rule? Yes, but I know in intuition level, what do you do? How do you actually handle chain rule? You have to find out. So loss is nothing but an equation of weights. You have to find out all the intermediary places where all weights is touched and do a partial derivative of it via this mathematical equation of chain rule, right? Right. So we've also looked at something very interesting. Any neural network optimization, right? Essentially neural networks are function of a function of a function of a function, right? You can express in that manner, and they are generally differentiable equations, right? Right. We have looked at few of the Let me share my screen because I think nobody's asking for it. So let me anyway share it. So we have looked at few of the um, let me just open the chat window. Just one second. Okay. All right. Okay. So do we remember what is the basic construct of chain rule? Just basic construct. We will actually know. There was a question that can we go detail, that we will do on from the maths angle. Maybe next week we will have time. But what was the basic construct of finding derivatives of each weights against lost? If you have lots of function of function of function, d of that function to that next derivative, and so on and so forth, right? So that construct has to be clear as well. Okay. And what do you mean by an epoch? Have you gone through this? We have trained a neural network with a Keras, with our one of our framework, which is Keras, right? And we have used argument. Epoch is a cycle, right? Cycle of what? If you can explain it, what is it? It's a cycle of what? Cycle of training. Okay. What does the training corresponds to? What are the steps that you have to do in training? Three fundamental steps that you have to do, right? What are the three fundamental steps? One epoch consists of one forward pass plus one backward pass plus one applying the weights via an optimizer, right? So one epoch is generally considered of one forward pass and one backward pass. Remember that, okay? So it consists of both of this one, right? Okay. Why do we need them? Why do we need epochs? Priyanka, the question is, why do we need epochs? Okay. Why do we need epochs? Because the intuition is very clear, right? You want to learn how to drive. You don't do it only once on the road, right? You have to do 2, 3 times. Why? Because you have to understand the landscape of, even if you're training, or even if you're driving, trying to drive in one road, you will do it multiple times, right? On the same road, right? Just to get better, become better at it, right? Now you can also complicate things by saying that why just one road? Why not different roads? So now, as a part of many epochs, I can also pick and choose various samples of my data set and pass it via my model, sorry, my training cycle for the hidden layers to get exposed to that data set and understand the data much better, right? One cycle is generally never enough for anything that you want to learn, right? You want to get better at it, right? And accuracy is what? What is an accuracy measure? Where we will use, where we will use accuracy? How we will know that we are getting better? We will check if the accuracy is generally dipping, or if you can actually specify an argument in the fit, right? In the fit we can actually provide an argument called as a validation set, which ensures that, which checks whether the model is actually getting better or not. And that validation set is carved out of the training sets. No, epoch is just a cycle. It has nothing to do with more hidden layers, or hidden layers construct your neural network architecture. You can have 3 hidden layers or 300 hidden layers. So if your architecture says that you have 3 hidden layers plus 1 output layer, so one epoch must be going from whole input to it must perform the full backward propagation plus a full forward as well as a backward propagation. Okay, that is one epoch. Okay, and we will run many epochs. And yeah, iteration is so iteration is good. Iteration is a term. You can consider that iteration not to gather more data. Okay, why do we run to learn more varieties of the things that is happening in the data, to gather more relationship that exists in the data. Okay, more information, we have to extract more and more information from the data, right? So that is why we actually go via many epochs, not just one. One is never enough. How many epochs can we go? How many cycles of iteration can we go? How many total cycles of epoch that can we go? Trick question, guys. Don't worry. There is no answer to it. There is no, yeah, essentially as many as required, right? But if you learn too much, what happens? Saturation of loss function, right? So if you learn too much, what happens? You will overfit, right? So if is overfitting good? It's not good, right? Overfitting means what? If something is overfitted, how do you know that a model is overfit? What will tell you that a model is overfit? It's a it's a problem that you have to deal with on a daily basis, right? If you are building in the business of, yeah, it's very close to model in accuracy, right? Very, 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 very close, right? Unexpectedly close, right? And what is the other way? You can also draw a graph of accuracy versus epoch. Remember that graph on a two dimension, right? You will be able to see that there will be a deviation at some point, that the model is continue to train, but while the validation data is actually failing big time, right? So what is important is that 100% accuracy on what? Okay, it does train accuracy on both the things. You have to understand that when you pass the validation data, if you remember the fit. Shall we actually look at that? Let me actually bring that portion as again. So practice lab. Okay. So if you remember, right, yesterday when we ran this code in our assisted 2, right? Let's directly go to our model fit, right? This is our model fit. Lots of information is here. I have passed my X train and Y train. I've told a batch size. Batch size indicate what? What is the batch size indicative of? There are two things, okay? Training set, yes. How many number of data points that you should be taking? Yeah. So how many? 32 would indicate how many number of data points that I should be taking for each epoch, right? And I have 20 epochs. So you can see this. This is called a validation set, right? You are training on this for the small batch size that you have provided here. However, you are testing against this. So you will try to see a line like this, right? It's a very classic line, right? What will you see? If you try to project your training and validation loss, you see this logs, you can see this. They always project, this is your training loss, training accuracy. Validation loss, validation accuracy. You have two metrics, right? So you can store all these things. So this is nothing but a history object. You can store all these things and you will see something like this, right? So you will continue to train really good. So this is your accuracy. So this is your epochs, okay? And this side is your accuracy, right? And somewhere it's like this is the loss. This is the loss. This is your epoch, okay? Right. So and suppose this is your training set, right? And are we able to understand this? And this is my validation set loss. Some point it goes here, which is this is the point. This point, my validation is no more, as the epochs are increasing, the validation loss is going up. However, I am still training really, really well. So I have now started memorizing. So this is an important way to realize. Okay. When you say 100% accuracy, you have to be clear on which accuracy are we talking about. That is also you have to be worrying about. So have a look at this. This gives you always 4 values. If you pass a validation set, it will give you 4 values. Okay. Right. Awesome. Good. What else did we do? Okay. We what do we remember? Okay. What is a dense layer? What is dense? What is this dense class or dense object or dense? Yeah, I think class. How do you define? It's a fully connected layer. Okay. By definition, it's a fully connected layer, right? The first layer is Of course, a hidden layer, but so essentially it means that it's actually a fully connected node. Dense means that it's a fully connected layer. Remember that, okay? And okay, what is dropout? Do we remember what is dropout? Or you can also say a deeply connected layer. Okay, someone also, if it, in short form it says that FC or FC1, right? So what was dropout? We have gone through a lot of things, so I think it will be easy for us to revise. So what was dropout? It was a technique of regularization. Can you guys tell me why are we putting dropout here? Typically, you know, typically, why are we putting dropout as a part of a layer? Can you think and tell me? Yeah, yeah, of course, yeah. At the end, the objective of any regularization is to overfit. But why it has to be via a layer? Why do you think a layer has to be added? I could have said something like this, right? I could have said here, like my regularization is, something like this, equals to, say, dropout algorithm, right? I could have actually said as my compile time, isn't it? Instead of that, a layer might, so instead of that, why are we doing it here? Okay, that is something also to be realized, and you will see that there is a value in doing this. I can actually, if I transform something like this in a layer, then I can actually apply at each of the hidden layer and not just at the compile time. Compile is only to build after the whole graph will be built, right? So I can apply inside my architecture itself. What is the, so this is a very important construct that most of the things you will see as will come in layers. Why? Because it is, you want, yeah. So what is dropout? Dropout is a way to regularize. Dropout is a way to regularize neural network. Okay, neural networks, as with any other machine learning algorithms, tends to overfit, right? So you have to ensure that the way you do it is that you sometimes switch on, switch off the neurons. Okay. So if you switch off some neurons, essentially when you switch off means the output of that neuron will be zero. So in every epoch, randomly 20% of neurons will be switched off. Every epoch, randomly, if you are running 20 epochs, the first epoch maybe 20% of random 20% neurons will be switched off. So for that particular layer, 20% neurons will have a output as zero. Next epoch, some other 20% will be switched off, right? Not any significance. Yeah. No, no, it's not. You can actually, you can actually tweak this thing. But yeah, of course, this is anywhere. This is a core neural network concept. So Keras is what? Keras is a implementation, right? Where any neural network framework that you use, you will have a dropout implementation. You will have an architectural implementation. You go to PyTorch, Caffe2, or others as well, right? TFLearn on Keras is on TensorFlow itself. You will have a implementation of a dropout layer. All these layers have a research around it, and people have computed and found out what it is. Implementation is Keras, so you can have your own implementation as well. Don't worry about it. Right? Okay. So what else did we do? I think that's about it, right? So did we remember what was this? We also went through loss function, cross entropy. What was the fundamental way? What was that cross entropy did for us? Fundamentally, what it does at a base level, what is try to do? You will remember, cross entropy tries to compute a distance between two things. What are those two things? It will try to find a distribution between probability distribution of my true value distribution versus my predicted value, right? And if the distance is high, my loss is high. So understand cross entropy very well. It will come in layers. Each of these things will come in layers, and you have to spend some time if you're going to create a production grade neural network model. Okay. Great. Now your neural network trained. However, we still have one important piece to go. So let's start our session today. Okay, it's gonna be mostly theory, and I have also, forwarded in case you don't have access to the assisted notebook. I have still again I have forwarded it to LSM. Okay, um, and I hope you'll get the email in case you don't have access. So essentially, if you go to self-learning, what we are starting lesson 5 today. Okay, we have completed lesson 4. We will be starting lesson 5. We will start with optimization. So we will be spending quite a bit of time on optimization algorithms. We will be discussing them. Okay, and then we will actually go to this construct or a one more layer called as normalization or batch normalization or batch norm. Okay, and we will look at an implementation of straightforward simple implementation of batch normalization, and this is the notebook that I've actually shared with you all if you don't have access to 5.4. Okay, and we will actually also look at transformer is not part of the syllabus, but transformer is not part of the syllabus. Transformer is from transformer is what? It's a neural net. It's an architecture which uses um, you know it's a different kind of architecture. However, its implication, it's not only language. You should know that there is a lot of transformer computer vision model, okay, are also coming out lately. Okay, transformer is not only language. It's not only language translation. Transformer is a fundamental new way of looking at it, of looking at new neural network. It's a class of neural networks whose architecture is a little bit different, okay, than the classical ways. But it has application both in language as well as in vision, which means it's a general purpose um, architecture. Okay, um, one of the famous transformer architectures name is BERT. Okay, it came out in 2017, late 17, 18. And Google queries, if you see, all the Google queries actually go via transformer. One really large BERT instance that they trained. Okay, transformer was done in Google itself. Okay, right. So this is lesson five's plan, and we will see. We are not in a rush. We will do this thing properly. If it spills over to the next week, so be it. It's not a problem. Okay, but we need to understand optimization algorithms. Okay, and we will try to do the best judge of how much we can understand with the given curriculum that we have. All of these are deep topics. There are reasons, and we will discuss them in the way that we can. Okay. The good thing about this is that we have lots of documentation to help us. By the way, before I start, have you actually looked into this? Have I shown you this? Playbook.tensorflow.com. It's actually a good site. Okay, playground.tensorflow.com. You should go this. It's a pure play, JavaScript based project, which visualizes what generally can happen in a neural network. Okay, it's also a very I'll drop the link here. Play around it, understand it. It gives you a very good understanding of what generally happens in neural network. Okay, in fact, this is an inspiration from another popular blog from this person called as Andrej Karpathy. If you are aware of who he is, do you know who's Andrej Karpathy? So you can actually, write something like this and visualize. Okay, understand. This is a pure play JavaScript based program. Okay, and it helps you to, understand how things are visualized. Okay, you can actually add your own code. Okay, and change the network and get this thing. This came out pretty some time back. Andrej Karpathy is Tesla's chief data scientist, right? He's the one who's leading Tesla in its build to create self-driving cars. Okay, right. I think this is also you should actually you know so this also you can, yeah. So this also you can see. This is also a good playground to understand how the neural network behaves. Awesome. So let's start with our class on neural network optimization strategies, tuning, and interpreting. So by the end of this lesson, what we will know that what are the various algorithms for optimization that we have. We have already named quite a lot. I have seen RMS prop, Adam, NADAM, okay, or NADAM, right, and so many others. But we'll actually go a little bit detail on them and try to find out how they help, and then we'll try to ask ourselves the best question that we always ask: which one to choose? Because with anything else, in almost all of machine learning is overcompensation of something, right? You have a lot of things to do for a problem. The question is that how do we choose which one to use? And we'll at least in the landscape of optimization, we might have some answer. Again, that answer is based on experience of other people, large collective intelligence of the whole world, right? So what is optimization? One thing is very clear. Okay, this is a very important aspect of a neural network, right? It is about choosing the input that is best possible to obtain, right, as a best possible output. By virtue, this term is very clear to us. We always try to optimize the best route to reach office, optimize the fastest way to study, optimize the fastest way to score runs, and so on and so forth, right? Optimize the field placement in a cricket match, and so on and so forth, right? Our life is all about optimization generally, right? Because there's always a goal, right? And to make an optimization strategy, you need to have a goal generally, right? You need to know what you're trying to optimize. In case of typically this kind of problem that we have, right? How do we design? What is the best optimum way to carry maximum load, right? Should we put 3 hoops in a bridge or 4 hoops? Should we put this extra rope? And where should we place all our objects in a warehouse? Right? This is actually a very, very important, tricky problem in malls, big malls, right? In the super stores, where you go, right? There is a science behind how the things are placed, right? And why do you see something in front, and why you have to find for some other. So that's also an optimization strategy, right? And they are all driven by some sort of algorithm. But in our case, we are generally trying to optimize. What are we trying to optimize? What exactly are we trying to optimize? We are trying to optimize the loss, right? We don't like to lose. Our loss function indicates that we are deviating from our actual value. Since it's still a supervised learning problem, we will say that how can I learn best? What is the best mechanism of my learning, right? And one of the things that we can do is with the understanding of loss function that we went through yesterday and in our machine learning itself, is that loss functions on its own might have this kind of a structure, right? Some loss functions, if it is only squared, they will be looking like a parabola, right? But in case of neural networks with really large sort of landscape that we have, it might not be one parabola, it might be a valley where you have lots of dips and lots of highs, right? So if you look from a valley's point of view, we will try to look for what is the lowest point that I can reach, right? You can also flip the question. There's nobody stopping you. But only thing is that the problem then becomes a little bit different. So a concave problem that you are trying to solve instead of a convex problem, right? We generally call this kind of points are called as extremum points, maximum or minimum points, right? And our objective is to find those extremum points. In mathematics, this term is called extremum. It can be either a minimum point or maximum. If there are, that is the question, right? That is the bane of this existence of this optimization, that if there is only one parabola, or if there is only one, if my loss function only look like this, I can somehow do something to reach to this top, or if you actually invert it, I can somehow reach to somewhere, right? But that's not the reality, right? right? So what is my reality? My reality is always generally like this. How do I actually, what is my loss functions look like? Sorry. Okay. My loss function is not that simple. It is, it goes like this and it goes like this, it goes like this, right? There are lots of, points where I might get stuck. But what do you mean by getting stuck? Are we clear on that point, right? Right. I've started from here, right? And I got stuck, and I think that I have reached my lowest minimum point in my whole of my loss function. And I have no visibility of all these things, right? Now, while I am traversing, I might not know, I might not be aware of that there are other lower points as well, right? That is one of the problems that we have, right? Since it's a function of a function of a function of a function, I don't know the whole of my loss function before I actually start computing it, right? And why is that? Can you tell me why is that? Can you guys just think that why do I not know the whole thing? Why do I not know the whole of loss function at the very beginning itself? You can say that why it is so hard. You already know, na, if you're trying to draw this at the end of everything, why don't I know this, that this is the lowest point? When a loss is computed against what? Do we realize that, right? Let's just go back to that practice code again, and it will be easier for us to know, right? So I am running this, right? Now, can you tell me loss is getting equated against what? Against a batch, right? Loss is always getting equated against a batch, right? And there is a reason that we do it because of compute reason. You can't load 100 million. If you have 100 million data set, will you be able to load it and run through it? It will take eons even to compute one epoch, isn't it? So we generally tend to load things in smaller things, compute everything, and store those computation somewhere, run the next epoch, then add those computation again, isn't it? Since we are computing in math, sometimes, many a times, it is difficult for us to get the visibility of what's going to happen, right? How is my loss, final loss function's shape might look like? It might have many crevices, right? So that is one of the problems. So these are called as, this specific point is always called, what is this point called as? If this is my lowest point, what is this called as? In the landscape of loss, what do we call this point? Yeah, this is, all of these are minima. But what is this point called as? This is a minima. This is a global minima. My objective is to reach to a global minima. But this is my local minima. That means that in this particular area, this is my local. In this particular area, this is my local. Now, if you remember, the loss, I've started descending from there, right? How do I start descending? What is my first point of starting? How do I start even? How did I even start my journey, right? So let's go back, right? Let's go back to our, our famed network. We did not know. Learning rate is used. We'll come back to that. So there is this confusion. Learning rate is not something that we start with ever. Learning rate is used when you apply this into the weight. Learning rate is an optimizer thing. So how do we even start from this point? We start from here, right? Loss is a function of weight that we know. So the first time, very first time, you've chosen some weights, right? How did we choose the weights? Did we even tell the model to choose some weights? None of the programs that we have done, we have given in weights, right? So what is the very first initial value of my weight matrix? It's a random, right? It's and you can start with zero, but that probably would not be wise, right? You probably don't want to start with zero, right? I mean, then everything is of same thing. So you start with some random values, right? And even the moment you say that there is random value, this is your starting point. So you can land here, or you can land here, or you can land here. There is no guarantee, right? In this in this step, you are not sure, right, where you're going to start from because it's random, right? Right? So that is the reason we have to. So we can start from anywhere. We can even start from here, right? And the moment even if we start from here, what will happen in the first backward propagation itself? We will know. When the first time we'll compute the gradient, we say that okay, looks like the gradient, this is the slope. I have to go down, so it will immediately come here, right? But whether you start here or here, you don't know that, right? Because your starting point is always a random points, right? So, so that is an issue. So let's look at what's an optimization algorithm generally looks like. And this will be very familiar to you because yesterday we went through this. So this construct or this equation, this is a very generic way of describing your computation loss. Sorry, or my optimization algorithm. J is generally called as my cost function, and you will see that J means, J is a summation of all loss across all my M data set, right? And what is my L? L is loss. Loss is loss per sample, right? What is my Y supplement or Y bar, right? Or Y hat, right? Or is basically this is my predicted value and this is my actual value, right? You basically give the loss two values, predicted and actual, and predicted can be expanded into that big equation, function of a function of a function of a function. Do we remember that? So this is a very generic way of describing my optimizer cost function. So when you say this is a cost function is nothing but cost function. Its loss is generally associated with per sample. You can also say what is the loss of the overall model, but cost is associated with always with the summation of all loss, right? So typically you will see this notation J lot of places. By the way, what is W and B? Are we clear? We forgot. We actually removed B from our equation itself. Yes, please remember, okay? We have bias, okay? Everywhere we have done, we thought that bias is not there, okay? Bias is there. Bias is per. Can anyone tell what is bias? Is bias per neuron or per layer? It's a question to you. Can you comprehend? It is actually per layer. Yeah, it's not per neuron. It is actually per layer. Per neuron, we already have weights. They will basically signify that how much important that particular weight is for that particular layer, and the bias will say that how much important that whole layer is in the whole network, right? That is something that you have to learn. It's possible that you have got a really bad layer which is producing really lot of nonsensical numbers. So the machine should learn that this is a bad layer and generally will be not that much productive, right? It is sorry. I have this cold, so I'm extremely sorry. But so this is what is weight linking to bias links to learn. Am I right? So linking wise, okay. So conceptually, yes. However, how do we actually interpret? You can interpret, yeah, definitely weight links to a neuron, bias links to other. If you actually say from a linking standpoint, we had this, right? What happened? So we have this, right? So what generally happens is that so what happens is that, so yeah, so what happens is that, so we'll put another neuron here. This is an empty neuron, okay? And we'll say that this is one, okay? Let's just remove this, sorry. I'm just gonna remove this and I'm bring it here, okay? So this is my empty neuron and I will connect this for every, I will, in fact, if you actually, let's go to the perceptron, right? Let me open up that perceptron. Just 1 second, guys. I will just open up. Just 1 second. Bear with me, please. File, and this was this. Yeah. If you can see my screen, right? You can see my screen. Sharing. I think I'm not able to see this, what I'm sharing. Let me actually, yeah, I think you're able to see my screen. Can you see this slide called as perceptron? Yeah, so you can see this is how a bias can be understood, right? You can put a 1, right? And we'll just put weight 0 here, right? And this is directly connected. So there is a weight 0, which is a 0th weight. This is nothing but the bias, right? So for every layer, we have another extra weight, which is nothing but the bias, and it is basically computed with 1. 1 is nothing but, just if you multiply anything with 1, it becomes the same thing, right? That's how it happens, right? It's an interesting take. but essentially do not forget the bias. We have one more layer of weight, that is nothing but the bias. So whenever we actually, sorry, so whenever we actually say this, remember we were actually computing what is our weight matrix. This could be, this is, this will be how many neurons? We might have one more neuron, right? So this is one per layer. That's how it, that's how you want to compute. Okay. So let's not forget about our bias. Okay, we don't need this thing. I'm stopping this, and I will. Let's go back to our optimization, right? So if this is our cost function, so value of cost function is the mean of all loss, right? Across, it's generally the mean of all losses across, all the samples. And how do we get Y prediction? Which path of neural network gives you Y prediction? It is the forward path, right? When you go back, when you do forward, you actually generate output that is nothing but your Y hat or Y supplement, okay? And with the help of optimization itself, we will minimize the cost function by updating. We would know, so backward propagation gives us the delta, the gradients, right? That how much we should change, and optimization actually does the change, in a way that is, if you actually go back to this, our landscape of thing, at this point, as we were here, and suppose there was a forward pass happened, we found out that there is some sort of gradient we found now, right? So we have to go down. So but how much, right? So this should be our new weight, right? But I have to know that I have to apply all my gradients or my updated weights from here to here, right? So that is what this journey is, what is being done by our optimization, right? How much I have to move all my weights so that I reach here, right? Because I'm going towards my loss. At least this is what the visibility is right now. As of now, gradient descent gives you this much visibility that I have some loss. I have, so there is a slope, I can go down. That is what it basically says, isn't it? So now this is the slope, I am going down, I have got my weight, and this application that I have actually traversed is done by my optimization, right? Okay. So how many types of optimizer? We see that there is quite a bit of optimizers, right? There's a lot of optimizers that we have. We have first and most fundamental optimizer is gradient descent. Okay. We will go through most of them. I don't know all of them or not, but we'll see in the slides. Sorry guys, I'm just drinking some water. Okay. So we have gradient descent. We have stochastic gradient descent. Okay. We have SGD with mini batch. Okay. And we have SGD with momentum. We have Nestro, accelerated gradient. We have AdaGrad, RMS prop, ADAM, and then we also have NADAM. NADAM is nothing but a combination of NAG and ADAM. Okay, and we already know, if you actually search Google what is the best optimizer for neural network, generally people will say ADAM. Okay, and we will actually realize that why so. Okay, it's not a black box. We will try to understand it intuitively, but why so. Okay. Okay. Quite a bit of, but this is not the end of optimizers. I have, if you actually see, people have, there is other sort of optimizers also. Okay, which is, so the list is pretty large, but these are the very popular ones. You will see good implementation of them in Keras as well, and Keras, or for that matter PyTorch, but we are focusing on Keras, and Keras gives you default implementation. We need to know the little bit of all of these algorithms so that we understand and appreciate that world started with gradient descent, but it was not enough. Then SGT happened, it was not enough. So there must be some problem. Then we've gone through this, up to top to down, and we've reached to ADAM, which is sort of working out generally well right now. Okay. So let's look at our first optimization strategy or algorithm, which is classical gradient descent. This is the vanilla gradient descent that we call. It uses The objective is remain same. You have to minimize the cost. I think we understand this very well, right? And you will realize that the term that learning rate, right, that you have been using, this is the learning rate that we use. Okay, this alpha, in some places you will say eta, or somewhere it will say theta, right? These are all the various notation, but this alpha is nothing but, sorry, this alpha is nothing but the learning rate that you can see here. Okay, this is the learning rate. So you can imagine, right, the learning rate, where you pass the learning rate, where will you be applying that learning rate? This is where it will apply. In a logical way, learning rate basically tells that how much should you take the step. What's the step size? Not I would not the step, essentially how much learning are you trying to put into yourself, right? So that is what the learning rate is. From an equation standpoint, this equation is very clear to us. Is it clear to us? This jw is nothing but my loss function. Okay, we have gone through the loss function yesterday, and this is my loss function. What is my loss function? This is my loss function, right? Loss equals to 1 by n, and this is actually now cost function. So this is my loss function, right? Along with my regularization parameter, and we'll come back to this in a bit. Okay, but this is my loss function. Loss function can be also expanded into this, and we have gone through this very much, right? So we know this. So j of w is nothing but exactly the same equation. Okay, and what are we doing? We are exactly doing dl by dw, right? So this is my dl by dw, this component, this is this component. Okay, this component is nothing but my you know partial derivative, or my gradient computation of loss versus all my weights, right? So that's what I'm do. I need to compute my loss, right? So so what I'll do is, like, I using this one. So if I compute dl by dw using chain rule, I have this value ready. So this value will be ready and given by my back propagation algorithm. It will be of size of that many number of weights that I have, per layer wise, right? I know exactly that if I compute this dl by dw in this specific scenario, okay, so I know, right, okay, that if I compute this specific scenario, that for this layer I have so many weights, for this layer I have so many weights, for this layer I have so many weights, for each of those weights, how much change I should be doing, right? So it tracks back propagation. What will do when it computes that dl by dw, it will ensure that it knows that for each of those waves, and it will store it somewhere, of course, right? It needs to have a storing mechanism where it will store, for the optimizers to kick in and use those weights and apply it, right? So for each of these weights, how much change? Some will change with 0.1, 0.2, 0.3, some will change with 10, God knows what, right? So your gradient computation will decide how, how much each of the weights will change. Is that clear, guys? I hope you are able to make some sense out of it, right? If it is not clear, let me know. This is very fundamental, okay? So this is classical gradient descent algorithm, okay? The same thing for bias as well. It's just easy to actually worry about only weights, because if bias is nothing but weights per layer. So all we can do is that we can add one more bias weight, right, per layer. So in this weight matrix of 60,000 into 128, we can have one more weight, right? So that is a way to imagine this. Okay. Okay. Are we able to understand it? Are we able to grasp things? I think this is I'm assuming that this is clear to all of you. If it's not, please raise questions. Okay. So this is exactly what we are trying to do, right? We are in this slope. We generally have to go to the slope. The slope is computed, and we assume that gradient descent assumes that wherever it is going, it is always a global minimum, right? It has no visibility that there is actually. Let me again go back to my loss function. It doesn't have any visibility that I have multiple global minimum. I've started from here, I can reach here, right? So that is what I am trying to understand. Okay. Okay. Have you guys actually downloaded from the e-courses? I've shown you yesterday all the PDFs. I think all the materials is uploaded there. If you haven't done that, please download from there. It will be an easy referral to all of you. Okay. So now what happens is that it encounters a global minima, right? So now there's a positive slope that comes, and again each side of it the same thing, right? If you have each side of it, it will actually go to the negative side, right? So, but the only problem with the vanilla gradient descent is what? That if it reaches any of the crevices, its job is done. It thinks that its job is done, right? It thinks that its job is done. It might, in our loss function scenario, in this case, if it reaches here, if this point reaches here, if you use a normal gradient descent function, it will think that it has reached a global minima. It will not make any more effort to cross over and come here, okay, because it has no way to and no mechanism to do it actually, okay. Guys, can you hear me, guys? Are you able to hear me? Just just ensuring that I have, yeah, okay, awesome. Thanks a lot. Okay, loud and clear. Awesome. Good. Okay, so this is plain and vanilla gradient descent. Can you guys tell me how do we know it's okay? How do we know it has reached global minima? How? Okay, so it, by the way, this is not a global minima, but how does it know that it has reached minima? So at this point, what will be the slope of the line? Zero slope. Perfect. At this point, you can have a zero slope. So essentially, first order differentiation will give you a zero slope. If you, the moment it has zero slope, there is no more other things, right? The next one will have a higher slope. So you're going up. You're climbing stairs. So that's it. Okay, don't climb stairs. This is the lowest point. You have achieved what you have to achieve, right? Have you used gradient descents anywhere else? Machine learning folks, people who have used machine learning, can you guys tell me, have you used gradient descent? If you have used machine learning in your work, in your classes, wherever it is, you 90% chances that you have used the vanilla gradient descent. Okay, because all the machine learning algorithms will have a gradient descent, right? This is the normal way of computing my score laws. If you use linear regression, how does it do it? The same thing, right? GD. So this is the classic algorithm that we use even in our machine learning also, right? And this is used in many other places to compute my lowest point in a series of lowest point, if I don't know the full function of it, right? Great. So what is the problem of gradient descent? Classical gradient descent problem is that, if it reaches a point, that's about it. However, it's very, very computationally, sorry, however, it is a very computationally intensive thing to, even if you have a million data points, think about it, that it is very computationally intensive. That's what I'm trying to say. Okay. So let's look at what is stochastic gradient descent. Okay. So the next better version of gradient descent is stochastic gradient descent, SGD. Okay. What it does is that, okay, it stochastically, the term stochastic generally means random. Okay. It takes random data points. It takes single data points to be taken into optimized weights. Okay. The mathematical formulation we will look, but essentially what it does is that data points are shuffled before the optimization, and some part of the random, no, its gradient descent is computed for some of the data points, not all of it, and resulting in some random weights. Okay, that is what, using that itself, you compute the slope. Okay, so in GD we use each and every data point. In stochastic gradient descent we use some of the data points, not all of it. Okay, right, some of the data points, not all of it. Okay, but point remains same. It does the same thing. The objective of stochastic gradient descent was to ensure that if you have a really large n or a number of examples, right, it might be very difficult to compute gradients for each of those things, right? So hence you have to ensure that you take some random data points and which goes into the optimizer, and then result into random weights. And that is why this stochasticity or the randomness you bring into this algorithm. Okay, it's little bit better, and computationally definitely better than normal GD. Okay, that's the vanilla. Again, SGD has multiple variations, and we'll look at it into a very important SGD optimization on top of it, right? So, but do we understand this part? Are we clear on this part? In fact, let me actually open one more Excalibur file that might be easier for us to understand from an advantage and disadvantage point of view. Okay, just guys give me 1 second. Okay, it might be easier to maybe what I can do is like I'll have to find it out. I will share that with you guys. This is created some a while back. What I can do is like that has like for each of these things I have is written in a way so that it is like advantage, disadvantage, that it gives you a clear way of how what to use, when to use, and so on and so forth. Okay. Let's talk about stochastic gradient descent mini batch. Okay, and this is actually a good combination of GD and SGD. Okay, which the objective of SGD mini batch, or it's also called as mini batch gradient descent. Okay, is that it solves the problem of really large data sets, right? Think about it, right? Gradient computation, in both SGD and in my GD, the gradient can only be computed after all the epochs are over, right? You understand that the problem that it can bring, because if you have a very large number of samples, you have to wait for all the epochs to get over to compute your gradient, and then only you can apply for it, isn't it? It doesn't work per batch wise, right? So SGD mini batch, and there was a question, right? Remember, I think yesterday there was a question that does it affect accuracy, right? SGD mini batch addresses those things, and while ensuring that it works on the mini batch size. Every time you say suppose that okay, my batch size is 128 samples at most, right? So generally that's what we do, right? 128, 256, generally not more than that. Even if you have millions of samples, you want to compute small, but not too small, small enough in such a way that you compute your forward, compute your backward, optimize it, and then add it continuously, maintain a moving average. Okay, so that's what a stochastic gradient mini batch does. It's a combination of a vanilla gradient descent along with our stochastic gradient descent, which distributes the whole training data into small mini batches. It divides the whole of training data into small batches, and that's what we have seen, right? In keras.fit, what do? We send the batch size. That is an important thing, and the SGD mini batch can actually work on only on that batch. Okay, so that way I don't have to wait for I don't have to wait till the end of my GD2, all my epochs to have some sort of gradient out of it, right? So what I will do is like I will per mini batch size I will compute, and then I will try to progress. Okay, so for example, the example is given neatly is that if you have a 400 training samples divided into 10 batches, right? Each batch has 40. The weight evaluation will be done iteratively 10 times over that many number of items, right? So, and that's an important distinction that SGD brings, and it works generally well. By default in Keras, if we actually use the optimizers, you will actually get this SGD mini batch, okay? Because you're anyway giving that batch size, right? Isn't it? Are we able to understand this? Okay. Are you guys with me? Let me know if you see any issues in the understanding. Okay. Great. So this is generally the, if you see like this, right? If you actually compute a normal vanilla GD and the mini batch, you will see that GD is very computationally intensive. However, so on the left hand side, you will see that, okay, So this is, if this is a contour map of your loss, right? You basically are, trying to draw a 2D diagram of your loss function. You are looking from top. Think like that. You are looking from top, right? Lots of concentric circles, and we are trying to go to, this is my minima, right? And at least in the vision of things, this is my minima. So GD will go very smooth. Okay, absolutely. And SGD, again, SGD has two versions. So this is what SGD mini batch is. So SGD mini batch, what the improvement that it brings to the table is that it will compute for that small mini batch per size. Okay, if you remember what we did in keras.fit, we have said that come do the whole training process in a batch of 128, right? SGD mini batch is any day, much better. Yeah, and that should be that is why, sir, anyway, it's a default. If you use SGD, right, it will be the default parameter. So what does SGD mini batch does? It will compute the gradient and sorry, it will not compute. Computation is already done in backward propagation. While your batch size is 100, in this case, suppose 400 training samples and 40 training samples, the computation is done by backward propagation for this 40 training sample, and SGD mini batch will apply those 40 training samples on apply and update the weights. Okay, so it will do per mini batch size. Okay, so that is what it will. This is definitely anytime better. So this is the definite. If you are using vanilla GD or only gradient descent style optimizer, your default choice should be SGD mini batch. And an intuition, like if you actually see this gradient descent, if you use vanilla gradient descent, when I say vanilla means by the default version of gradient descent, the first, okay, that's what we generally call if you say vanilla. So it will go very smooth. Why it is going smooth? Because it has the whole idea of the gradients, and which is computed only after all the epochs. In this case, right, in this case, SGD mini batch, the red one is SGD mini batch. It has seen that 40 samples. In the 40 samples will go here, and then the rest 40 samples and the other 40 samples. So it will have a lot of zigzag area. Okay, it will have it has lot of zigzag path. It can be noisy weights also, but generally it will definitely reach your it will reach your global minimum faster. Along with it is much less computationally expensive, because you're computing everything via mini batch. That's a very important idea. It's practical also, right? You can't have 100 million weights updates and cannot also wait, right? You want to wait after eons to update something? Not possible, right? So always work in batch, and this extends this idea that forward propagation is working in batch, loss computation is working in batch, backward propagation is working in batch. No reason why we cannot apply the batches itself and then somehow aggregate all the batches, and reach to our global minimum. So that is this SGD mini batch does. It is definitely the default choice if you are trying to use a vanilla optimizer like this. Okay. Okay. Now let's come to a problem statement. Now, but all these things are fine. Let's go back to my Excalibur. All these things are fine. It still doesn't solve this problem. All we are trying to say is that if I start my journey from here, okay, how fast can I reach here, and how computationally less intensive? GD will take 3 days, SGD will take 2 hours, SGD mini will take 5 minutes. That's all we are trying to say. Okay, so that this is a very rough comparison of things, right? If you say that if you start from here, GD will take a lot of time, SGD will take a little less time than GD, okay, and SGD mini batch will take lesser, and it's also be computationally much lighter. But none of this tells me that this is my global minima. It will make a mistake. Mistake it makes is that it will consider that this is my global minima because it has reached here, right? And this is vanilla gradient descent. Even if tries to goes up, what will happen? If you tries to go up, what will happen? If you are trying to use, you know, any version of GD, something has to have something. What will happen? It will that find that okay, you're going against the slope, then it will pull it down. There is no way you can actually go up and cross this barrier, right? You understand this part? Are you able to understand this part? Let me just take a different. Are we able to understand this? This is critical, okay, for us to understand momentum. So with any kind of SGD or GD, we will be stuck here forever, and there is a very high chance, okay, and it's pure luck because if your weight starts from here, you may reach here, okay, but you can't guarantee whether the weight will be starting from here, right? There is no guarantee that can be given. So in any SGD or GD, what will happen is that if it reaches the minimum, it assumes that it will be global minimum. It cannot ascend up. The moment it tries to climb up, it will be pulled down because the gradient says that you're going up. No, you can't go up. This is what it is. Your slope has to be. This is the minimum slope that I have found out, right? Or that is a problem if you have multiple such crevices, you have multiple such valleys. So with this, there's a defining point at for the optimization algorithm, which is what this algorithm brings is called as momentum, or its other way is called as, so by default it is just called momentum. Or you can also consider this as an SGD with momentum. Whenever you say momentum, momentum means nothing but SGD with momentum. Okay, momentum allows you, intuition point of view, momentum will allow you to traverse here, climb this, and come here with all the good properties of SGD that we have seen, or you can say SGD mini batch. Okay, right? Everything is mini batch now. So understood, right? Let's see what it is. How does it do it? Okay. But are you able to understand or appreciate the intuition behind what we are trying to say here? What does momentum allows you? Momentum allows you to reach. If you have reached here from SGD, you can climb up and reach to another global minima, which could be really a global minima, by using this additive or extra algorithm, which is called as momentum. Okay, if you use momentum is nothing but SGD with momentum. Okay, you have a stochastic gradient descent formula plus momentum. Okay, and the way it does is fairly intuitive enough. It's not very complicated. If you have done time series, did anyone of you did time series, or for I'm just trying to understand. Have you ever done a time series modeling? Or any kind of time series, even statistical time series. Do you remember we had a time series in statistics, right? Exponential moving average or any kind of moving average. The idea of moving average itself, right? And so that is what is being used here. And for you, so it's basically uses an exponential moving average or a moving average calculation. So what does momentum does essentially is that it uses a moving average calculation to analyze the data points by creating a series of averages over a different data sets, which is nothing but each of the batches, and it will try to compute this velocity. Essentially, what it will try to do is like it will, from a, if you think from a physics standpoint, right? Let's bring a completely different intuition. Is that if we reach here and if we have to push up, we need some sort of velocity, right? And we need to be very clear how much velocity we need, right? What is velocity? Velocity is nothing but I have to climb up. I need to give you a little bit push, but the question is that how much push should I give, right? And I have to give enough amount of push in such a way that I just cross over and again go back to my slide. So that is exactly what this term V can represent. It's nothing but a velocity. What it tells is that at the time step 1, basically at that first time step, I have my this is my data point, right? This is my data point, right? In my second time step, so like if you are analyzing last 3 days of stock market's price, right? Today's will be B1, yesterday's will be B2, and day before's will be B3. Considering that, then today's stock prices might have a higher impact from the one which was yesterday, right? And then there will be a higher than that impact from the one that is from day before. In other words, today's stock price generally has a decaying effect. You need some sort of damping factor for my all the previous time averages, right? Whatever your time gap is doing. So this is exactly how we sorry. This is exactly how we compute my moving averages, right? So I will compute a variable at time t1. This is my current time. I will compute another variable for my previous step, time step. Time step is nothing but consider them as the iterations that the SGD is doing, right? So at the time t, it found something, it stored it, right? So at the end of it, what it will get is that it will get a calculation like this, okay? For my v1, v2, v3, it will have for my v3, okay, I will have all my days. Suppose v3 is my latest, all my days time steps are continued, and v3 is my latest, v3 is my today, my latest iteration is my v3. So I will consider that as my most important value, and then I will consider a little bit of yesterday and really little bit of day before yesterday. So this formula exactly computes like this. This is how we actually statistically also compute moving averages in statistics also, right? And that's what momentum uses. It basically uses this formula plus SGD, right? If you actually see this, so this is the if you see this is my old formula of applying normal SGD, right? But this is my new. I have to apply my new weight. New weight is nothing but old weight, then a term on alpha, which is my learning rate, into my dl by dw or dj by dw, right? So that's what I do. Instead of that, what I do is like I add this term. This lambda is nothing but this momentum, okay? Okay, this is gamma, right? Gamma is nothing but this momentum value and this full expression till the time step, okay? This is it's a very important pivotal piece where finding this local minima, and it proved really good results, right? So if you actually go to Keras and Optimizers page, right, I wanted to take you guys to there, and you will see that, right? Let's go to SGD. So SGD, and you will see momentum is nothing but a attribute here, right? Right? So you can see that momentum is nothing but an attribute here, okay? So you can use SGD and you can just supply how much momentum you want to give the SGD, so that SGD is equipped with that velocity and it should be able to cross the cross that peak and reach to the true minimum, at least try to reach to the true minimum. So this is what the intuition is all about, right? And we will come to this API page, don't worry guys, okay? It is observed that this particular value works at 0.9, and why, how it is observed, there is a historical significance. In fact, the paper itself claims, the momentum paper itself claims that it is good if you can set this value at 0.9 by default. I think it is also written somewhere here, and I was seeing that. So who created momentum? This guy called as there was the paper. Where is the paper link? I think yeah, Ilya Sutskever, who was also part of AlexNet. Remember? Okay, he was also one of the. I think he was the one who created for Nesterov. He was the one, but let me just find out who was the one who created momentum. I'll send you that link. But this is an interesting thing that to know that momentum is nothing but a a parameter in my SGD optimizer. Okay. And if you actually see, right, I was seeing somewhere 0.9 is used generally always. Okay, most of the cases 0.9 just work. Okay, that should be it. So now what we did is that, okay, fine. So in this case we were able to somehow, let's come here, we were able to somehow, we are getting stuck from SGD and SGD's variation. Here comes this great algorithm or an optimization of the normal SGT momentum, which allowed us to cross here, and then everything else is hunky dory. So I can now cross this via pushing this, pushing my gradient and accepting a little bit of leeway. How I'm doing it? By ensuring that, by knowing the fact that, my old earlier time steps are providing something to me by computing this moving average component, providing the velocity towards it. Do you need to know the formula? Probably not. Keras makes these things very simple for you, but it is good to know, right? If you really are stuck in somewhere, the place where, it's going to be easy for you to debug better, right? Now you see, now what you will see that SGD with momentum will clearly show that momentum makes steps smooth and less noisy. Normal SGD will be very zigzag because of its, you know, because of its stochasticity, right? Its randomness. It will be zigzag. SGD with mini will be also very zigzag, isn't it? Because it is taking, you have stochasticity, which is randomness, plus you are computing per mini batch, right? So if you do like this, you will have a lot of, okay, you go here, again the gradient will come here. No, 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 I have to go here. Like this, it will be there, okay? But with momentum, you will have less, noise and less zigzagness. You might get a better smoothing, right? So by definition, use SGD mini batch with momentum, okay? And it should help you to overcome that, right? Okay, awesome, right? Any questions, guys? Are we all good? Okay. Let me also, I'll find out in the break. I'll find out. Um, there is this thing that I've actually, no, I think I did that. It was easy for, from an intuition standpoint, was easy for me to understand. If putting all of them in the same map. Okay, I will try to find out and send it to you guys. Okay. So the next algorithm that we can consider, this is nested of accelerator gradient, okay, NAG, is actually done by Ilya Susekar, who he was the one who actually created, part of that AlexNet, remember? Okay, and convergence of neural network was a hot topic, right? You can have so big networks, but it is taking extremely large number of time to converge, right? So it considers, it takes that same approach of momentum, but what it does is that it takes the interim velocity weight, which is basically used to calculate the weight with the help of this particular velocity factor. In fact, if you see, okay, in Keras, let's just go to Keras one more time. If you actually see, let me just go to optimizers, right? Optimizers will give you, right? So this is an Adam. Okay, so uh, and nested of is false. This is also part of a, if you apply this, so this, they will apply a nested of momentum. Nested of momentum is a little bit improvement on top of momentum, okay? If you, so it's interesting to note few things here, right? You can use SGT by default. That is what we were using. And in fact, if you remember in our practice lab, we did not even pass anything, not even a learning rate, right? If you don't pass a learning rate, it default to 0.01 in Keras. That's what it did, right? So this is default of 0.1. And if momentum is 0, it will fall down to vanilla gradient descent. You can see this, right? And if momentum is non-zero, then it will become the stochastic gradient with dampen oscillations. These terms are important. So dampen oscillations essentially means that it is computing that moving average over the time steps, right? Similarly, you can also apply Nesterov momentum, okay, by just turning this from true to false. Right? That's all. That's all one has to do. You do not have to know, but it is good to know, right? That's a interesting aspect for you to consider. Okay. Right? Okay. Any questions? So where are we? We will take Adagrad and other things post break, but we have about 5 minutes, right? Do we have any specific questions on till the time that we have done, right? So let's see what is the learning result. All these things still have a problem, and we will discuss this problem. Let's actually, in fact, let's discuss this problem. Any gradient descent style algorithm, has a problem in the drawback is that learning rate, right? Consider the fact that who gives the learning rate, right? You have to, first of all, you have to provide the learning rate, and second of all, this is a big problem that it's constant. Okay, the learning rate remains same across all epochs, right? And this was realized sometime later. One Nesterov came out that constant learning rate might not be good, in the sense that in this landscape, when you are going down, in some cases you might want to go a little bit faster, right? You can apply things a little bit faster, but you are unable to do it because this learning rate, that you can actually go faster because the descent is steep, but there is no way you can change that while the model is training, right? So this constant learning rate has come and haunted the SGD or classical gradient style algorithms, and we will see that how this was handled in the other parts of other style of algorithms. There's another problem that existed, is that sparsity of data. Gradient descent, if you have a lot of sparse data, and what is sparse data? You have lots and lots of zero. Okay, there's not too much data. Data is very sparse. Okay, maybe it's extremely large categorical data with too much. Like, even what is sparse? An image is a sparse data, isn't it? An image with black and white is actually a sparse data. MNIST is a sparse data. You have very little places we have non-zero data. Most of the data is zero, isn't it? We have seen this yesterday, right? So MNIST is a classic example of a sparse data. In generally, it's been noticed that a constant learning rate on a sparse data is not an efficient approach and does not result in good convergence, right? So this too was the being one of the important things which fueled next set of evaluations, and we will see that what was done to ensure that this constant learning rate and this ability to handle the sparsity, data sparsity, these two problems, how it was handled in the other algorithms. Okay. So let's do one thing. We are at 9:28. Do you think that we should take a break or we should just continue? Let me know. Okay. Maybe after the break, let's take a break actually. Let's take a break for 15 minutes, a usual break, and then come back and continue our discussion on optimization. Yeah, no, the thing is that all these things I don't have. The assisted practice doesn't have so the change is very simple. That I'll show you what is the change, okay? All these things is, code-wise is just one line change, right? Code will be very, you can see this SGD, put a learning rate, momentum 0.9, instead of true, false, done deal, right? So that's done deal, right? So that is one thing that we can do. But where do you have to do? If you have to come here, okay, you come here and basically change here, right? Your optimizer, this is the object that you have to clear, right? So you can change this. The code wise is actually very simple, simpler than the way we are explaining, right? Right? We'll come back to Nesterov, and we'll start from Nesterov. We'll again revisit on the and we'll come back to Nesterov. We'll revisit the problems of gradient descent, and then we can see how we can solve the other things. Yeah, let's do Nesterov also, right? Okay, let's go for a break and then come back in 15 minutes time. Okay. Yeah. Okay. Shall we regroup? Let me know, guys. Are we all there or not? Let's start. Okay. So, I was able to find out that uh, that file might not be it, this is an old file. So, and I'll share this with you. But this was done some time back. I don't think much has changed, but there could be typos and there could be typos. So what this does is that it just gives you that for each of these optimizers, right? Gradient descent. We've discussed gradient descent, stochastic gradient descent, gives you a formulation, what it means, and so on and so forth. And it actually says you these two problems. So this is what we discussed, right? Isn't it? And then, yeah, it's almost all of them are momentum, Nesterov momentum, and then the other types of algorithms. Not other types, but the. So basically, what we discussed is momentum, right? What did we said? Momentum was it was, it was invented because of reducing that noisiness, right? And because that, if we can actually move up that, that ascent and go over to that local minima, try to find out the global minima, right? SGD, since it's noisy, right, it zigzags, it has very high variance, okay, right? And I hope you are aware of what is variance and standard deviation, right? So it has high variance. So momentum was that, and what does momentum did? Momentum actually reduces these oscillations really well, right? Momentum converges much faster than the vanilla gradient, as well as SGTs, right? Normal SGTs as well. One of the disadvantage of momentum still remained was that hyperparameter, right? That that learning rate parameter was a problem, right? Because it has to be manually selected. That learning rate of 001, and then momentum had this parameter as well. Okay, so that was also an important thing for us to remember. So this parameter has to be manually selected, and it has to be little bit accurate, right? Nested of momentum, it is basically the problem of momentum. It's actually on top of momentum, uses only on SGT. What momentum may happen is that if your velocity across that particular loss graph, if your loss graph is like this, right? Remember, my loss graph was like this, right? And this is my global minimum, and I am here. I've started here and I'm here. It's possible that I actually may cross it, right? It might be too high, and I might even may miss the local minima, and I may continue to rise. So I am here, and my momentum is so high, then I might actually cross this and push come here, right? So that is what Nesterov accelerated gradient wanted to avoid in momentum. And these are all an iterative process. People were actually, when they were trying with various optimizers in large data sets, they were finding these problems, and they are solving it one after the other. So what NAG did, or Nesterov accelerated gradient did, it that it is a look ahead method. It was trying to look in the future. Okay, the objective was, it was trying to look ahead in the future, okay, and basically modify the weights so that basically it tells you a future location. It's pretty neat in that way, okay. So now what we'll do, we'll calculate a cost based on this future parameter. It's okay, rather than the current one. It approximates that, no, I should be here, not here. right? Something like that. Okay, I should be here, not here. It tried to approximate and estimate a future position in the gradient, and then applies that, sort of in a way that, okay, you are not supposed to go beyond that. You do momentum, but that's your end goal, kind of thing. Okay. But good thing that happened with this particular algorithm, the mathematical equation is this. Okay. And so this part is momentum, right? This part is true momentum, and this is the Nesterov part of the things. Okay. So theta is nothing but any learning parameter can also be called as a theta, right? All the parameters or w's, right, are can be also, most of the time you will see in papers and in explainers, they might also use theta for that matter. Okay, so theta is just nothing but w for us, right? So this is the equation and a mathematical formulation of it. One of the advantages that Nesterov gives us is that it will not, it will not miss, it doesn't miss local minima. Okay, and it basically, since it tries to look ahead and project itself, it will slow down. Okay, what will it slow down? It cannot slow down the learning rate because that's constant, right? For all these algorithms, remember, it can slow down the momentum parameter, and instead that, okay, reduce your velocity, because you can detect if there is a minima is approaching or not. This is like pretty nice. I think it is very small, right? Let me actually increase the size of the screen. Okay, I will clean this thing up and send this to you. It helped me a lot when I wrote it down. I must have done it some time back, but I will clean this thing up. I will see that there is no obvious mistake, and I'll share this nodes to you. It will be easier because there's just so many optimizer functions. Again, what is the major disadvantages? This selection, hyperparameter selection, manual selection is not an easy thing that to achieve. Achieving that right hyperparameter requires, requires a next level of exercise, expertise, right? So it wasn't easy, but that is what NAG or Nesterov momentum, so Nesterov accelerated gradient did. Okay, we will continue in this slide. So now one thing was very clear, right? All these six algos that we have gone through, six optimizers, had two problems, and this we have seen in the slide also, right? The learning rate was always constant, right? To choose and right, choosing that right learning rate is not a easy thing, right? It's like if you choose a very low learning rate, what will happen? It will take a long time to converge, right? If you take a very fast rates, then your weights will, the basic equation of weight uses the learning rate. You have to apply that, right? If you have a very large learning rate, your weights will change drastically, and you might actually overshoot that lowest point that you want to achieve, right? So it's not an easy task to know what is learning rate, right? And this constant idea of this constant learning rate might not be good. Then the sparsity versus the density of a data might also was also causing a lot of problem, because most of in an image, especially we saw in MNIST, most of them were actually zero, if you remember, right? So what was done? So this is another class of algorithms which was thought through, and they started with something called as an adaptive gradient, okay, or in short form, ADAGRAD. The idea was very simple. Constant learning is a problem. We need to do something about constant learning. So this changes the learning rate itself, okay, and what it does, it changes the learning rate. So for every such parameter, okay, so for every epoch or every time step, the learning rate changes. This is pretty nice. Like whenever you compute your gradient and everything, and you know that you have some idea, right, what should be your next learning rate. So that is what exactly what it does. This is also a second order optimization problem, right? We will not go into this. The world of optimization is a deep topic. Now, if you actually, I highly encourage you to go through this first order optimization and second order optimization. Second order optimization is nothing but derivative of derivative. Okay, and how do you know that you are actually in local minima? How do you know that you have come to a region of global minima, right? This is a problem that people are trying to solve for a long time, and we have a method of specific method on second order derivative called as Newton's method, but it is I have not seen much. People don't use it. At least I have not seen. Maybe it uses in by used in really large places. But you can look at it. Okay, you go to YouTube, you will see what is this first order derivative. Whatever we are doing is nothing but a first order optimization problem. Okay, so AdaGrad is one. This what it does is that it basically keeps on changing this learning rate after every time step. And it makes very frequent updates. It makes big updates for less frequent parameters and small steps for frequent parameters, right? It will try to find out places where it has to make large update for those weights, okay, because they are changing. Though some weights, like you have so many weights, there might be some weights which change very less, very small. In so small, the gradients of those weights are very small, and some weights the gradients are big, right? So what it does is that for those weights where gradients are extremely small, it will make some big updates because they are approaching some sort of staticity, right? But where gradients are really large, it will reduce the rates, and it does it really intelligently. So that is AdaGrad, okay, and AdaGrad was good actually, okay. So learning, so this idea, and then it flourishes three or four things, and we will see that the Adam is nothing but a precursor of the postcursor essentially of this itself, right? Here it changes the learning rate for every time step. We don't need to manually tune learning rate. So this is important, right? At least though Keras, you will see, we'll go to Adam, we'll discuss about this, but you don't have to do too many hyperparameter tuning in this learning rate. But though you probably have to give a start learning rate, okay? You might be able to say that start, okay? Start from this learning rate at least. It is also able to train on fairly sparse data, works better. This is computationally intensive, okay, but however also the learning rate is generally always decreasing, right? Because for every time step the learning rate decreases. Now the decrease of learning rate causes slowness in training. This is one of the big disadvantage of AdaGrad, okay. We can move to the slides, but I think let's continue, and then we'll do the review of the slides if you have missed anything or not, okay. This is anyway an intuition behind all of this, and we will see in practice. The code is just one line. I'll show you what you have to do basically, right? But code will show. We'll definitely go to the code, okay. So what is AdaDelta? AdaDelta is just an improvement of AdaGrad. It's an extension where if we try to remove this problem, every disadvantage has spawned. Every time there was a disadvantage identified, okay, this spawned generally a flurry of activity to improve the disadvantage. Now, learning rate decay is not an easy problem. It's a complicated, it's a difficult problem. It's a major problem because if you have a decay in learning rate, what will it will lead to? It will lead to your gradients will become stagnant, right? At some point in time, right? You are learning slowly and slowly. Convergence will actually go up. So that is the bigger problem, right? So that is what AdaDelta tried to improve, and what it did is that instead of accumulating all, so basically try to remove this decaying learning rate problem, okay. And if you see AdaGrad uses a square, okay. It used to store, this is the core equation of it, where it's tried to store the gradients, okay, for up to a time steps t, okay. And if you actually, then this is explained nicely in here, okay. Let's go to I've gone to the slide now. If you actually look at AdaGrad very carefully, the equation, the mathematical formulation is like this, okay. For every new time step, so this is my equation. My alpha star is now it used to be my learning rate, right? Now no more. So this will be computed by the model now, or learned by the model. I will start with an initial learning rate. The formulation is like this. This is my initial learning rate divided by, beta. Beta is nothing but the square of my loss, okay, per time step. This is my square of my loss function, nothing else, okay. And since, what is this epsilon? Do we know what is this epsilon? Anything that you will see that you are to divide by something, we will put a very small epsilon so that the denominator never becomes zero. It is a mathematical, you know, construct, so that it ensures that, that your denominator is never zero and you don't reach an infinity. Anything divided by zero causes problem, right? You will have a problem. You might actually have nans, right? So what it does is that this is the formulation. What it does to generate the learning rate. However, you still have to give an initial learning rate, and then basically square root of cost square or loss squares plus some epsilon. This is what ADAGRAD gives you, okay? And it's a very small non-zero, so this is what the epsilon looks like. Right? The only drawback of ADAGRAD is that many a times this square term, the bt or the beta t, right, is nothing but a square term. It might become extremely large, very, very large, right? Now, if it becomes very large, you can imagine what happens. The denominator will become very big, numerator has become very small, hence the overall learning rate gets smaller and smaller. That is the reason ADAGRAD per each epoch learning rate tends to gradually decrease. Okay, I hope you are able to understand what I'm trying to comprehend here, right? So that is one of the reasons why you will see a gradual decrease in the learning rate, right? So this is exactly what, so we have directly moved to RMS prop. So ADA delta actually tries to improve upon it. I will move to the Excalibur once, okay? And if you see that, what did ADA delta did? Instead of accumulating all the squares, it was actually accumulating just the past gradient. That's it. It's basically limits. Sorry, it will limit the window. It will not take all the squares till the time frame. It will say that only give me last 5 or last 3. Okay, past gradient, and that's about it. Okay, so that is, it will limit by this. Okay, however, it was still not highly optimal, and that's where we found out RMS prop. What does RMS prop does? Okay, RMS prop actually focuses on this term. Let me actually shift to the PPT again, and you will see what RMS prop does. The equation looks exactly same, except that there is no, the square term is actually replaced by this term, which is a average, weighted average. Okay, and this ensures that the denominator does not become extremely large, and hence the overall learning rate is actually in some boundary. It doesn't decay too much, okay, and doesn't have a really large decay, right? So in a sense that RMS prop is pretty good in the sense that it solves the problem. RMS prop is that, again, that line of adaptive gradient kind of an algorithm where it solves sparsity, and then it solves. So this is a non-constant. It's not a constant learning rate, right? It's trying to learn the learning rate per epoch, which is very good. And it also solved. What did it solve? It solved the problem of previous optimizers of this class. The problem was decaying in the learning rate. That is also handled by this equation. It's no more squaring, right? And then, but so that's what it. However, that is what leads to this particular. No, so performance wise, so I think performance. Are you talking about compute performance? I think both are equally intensive. Okay, and the problem with ADAGRAD or ADA delta, right? ADA delta will be both are okay. I think ADA delta is little poorer, inferior than RMS prop. So ADAGRAD came, then there was a little bit of increment on ADA delta, and then RMS prop. So if you have to choose between ADA delta and RMS prop, directly choose RMS prop for sure. Okay. If you have been given a choice between those two, please choose RMS prop. Okay. However, after RMS prop, we come to this algorithm called as ADAM, right? Which is what we wanted that goodness of momentum, right? That momentum was good, remember? Momentum was giving us, you know, pretty good thing. However, we also need the goodness of RMS prop, right? And this is a collaboration between these two algorithms, and this is right now sort of the state of the art algorithm which is probably used in in most of the things. What happens is that you will see that the first part is exactly like RMS prop, right? This part, this part is nothing but RMS prop, and it is multiplied by a momentum variable. Right? This is coming from that momentum. But this second term is nothing but the momentum variable, right? So this is a joint. You can assume that this is actually a conjoint, two different algorithms joint coming and helping together. This is fairly fast, one of the fastest, and of course converges very fast, and solves all the problems, right? And solves the problem of variable learning rate. You just have to give a start to it, right? You don't have to give for every time frame. Sparsity problem, momentum was good, right? If you're stuck in a local minima, you still would need some push to go to the other side, right? That also is there. So overall, this is a good algorithm which can, which you can use, by definition anytime, right? Um, uh, Sorry, I think we cannot generalize anything, but most of the time you will see that people will use by default Adam. Okay, and the reason why they will use Adam is because of this properties that it tried to solve, right? You can imagine what is happening, right? The amount of effort that has gone with just building the neural network, and the amount is pretty large. And you can see that the for the quite a number of papers as well as on each of these optimizers, right, are being built, because it's not just enough to know that you have computed a gradient. You need to apply it in a way that it is computationally, reliable, right? So this method is very fast. It converges very, fairly fast. Okay, rectifies that learning rate, has high variance, which is good, and though it is computationally expensive, but you know, that again, I think everything is almost computationally expensive. This was done some time back, and I probably have copied it from somewhere, right? But I think this is an acceptable, expensiveness that we have to do. We have been running MNIST on Adam. It was all fine, so it's okay. I think it's Adam is definitely one of the best out there. The question, so yeah, so very clear. How do we know how to use? By definition, just go with that. So if you are okay, if you have a data set which is dense, if you have a data set which is sparse, right? This is one easy, very easy, decision kind of thing. Is your data set dense? Can you consider your data set as dense? What is dense? You have lots of empty areas, which is zeros, and only few places you have data. MNIST is a very classical example of it, right? Right. If you are dealing with X-ray images, think about it that you are doing a COVID X-ray images, chest X-ray, and they are mostly black and white, right? And there's not most of the images will be in black. Only the parts where the X-ray is done is so you can consider that as a sparse kind of a data point. Each of those images are like that. So that is one important deciding factor, isn't it? If you have to learn faster, how much compute you have been given, generally by definition go with Adam. Okay, but that doesn't mean that okay, let's look at this way. If you have all the time in the world and all the compute energy in the world, which algorithm will you use? One thing is very clear, right? Let us go back to the PPT and see one more time. Yeah, perfect. Why? Sorry. Why? Because if you have all the time in the world and everything, then because it takes a lot of time. Let it take. So suppose suppose you have no problem with time, no problem with compute. That's what has been given to you. You know that the best gradient computation can only be done if you look at everything, right? Every part of the data, that if that has been looked at, right? So your smoothness, no one can beat like this, right? It's very smooth. It will take its own sweet time. But the practically will hit when you say that I don't have so much time. It might take years for a problem statement to write. The rate of innovation only can be increased if you reduce the time you spend on it, right? So that is what it is. You can take your car and train and train and train in each of the road and say that I'm never done after 3 years also. We generally don't do that, right? We try to optimize our time. We said, okay, even if we are now we have reached somewhere, let's go and start running, right? So think from that point of view. Classical vanilla gradient descent is still best, but it is impractical. It is not possible, right? You still have to work on mini batch, cumulatively work towards it. You have to ensure that your data noisiness or sparsity should be handled both for the dense as well as this, right? And it's basically use case by use case. So that is what it is. Which is the best algorithm? I would say that start with Adam, okay, and I think that generally gives you a good base to start with. In fact, if you actually go to Adam's documentation, right? Let us just quickly go to Adam's documentation, right? Where is Adams? So you also have, yeah, so I use something called as Adamax is also there. So you can see this Adam documentation, and you can actually look at the paper by Kingma, okay? Kingma and Jimmy Lee, I think. Sorry, Jimmy Ba, right? So they are the ones who actually, you can look at this, and you can see the paper, and this you can see this, right? It's not a it's you know from a timeline standpoint, it's just 7 years back that has come, right? So in the sense that we are seeing new age algorithms, right? And where was this done? So Mr. Kingma is now in OpenAI, right? And this is the University of Toronto, Jeffrey Hinton's lab, I guess, right? So this is definitely Hinton's lab, right? So this is fairly popular. No, this is the method. So you can read through this, and you will see that what is been told here, why it is good, and this is a 2015 paper, right? Given the fact that 2015 is the start of the maybe 3 4 years, right? It's pretty amazing, right? And these are all new age papers. Okay, you wanted to know how to do the code. Let us do one thing. Let us quickly see what is the code that we have to do, right? Um, I know that today's talk is a little theoretical, but the thing is that you cannot escape this thing. Okay, a little bit theory is important, because if you do not understand the problem, then again it goes to that problem statement of GD. Do you want to face always the problem and then come back and solve it, right? So that is the thing, right? So now you have enough idea what is what, and you know that my base should generally be Adam, okay, to start with. And if you have Adam, you'll generally be getting a good result. If you see the paper, they will publish, right? They must have used in various use cases, not only just not only in one places, and this is all mathematical formulation. Everything is given, right? So you can say that convergence matrix of Adam, okay, using a proposed. So I wanted to show you that what data set that they used and what is the optimization that they used. They use AdaGrad and RMSProp, right? So this is actually on top of RMSProp, which came and from version Momentum. So basically, Momentum was from this 2013, right? So you can imagine that these are all fairly new age papers, came in about 10 12 years back itself. I was just trying to show you the data set you know that they use to test it. It's not clear. There is also a diagram where you will see diagrams like this. Yeah, see, you can see. Let me just increase the. So you can see in MNIST, right? MNIST. This is an MNIST multi-node. We are very familiar with MNIST by now, right? If you read this piece of graphs, this is iteration over data, entire data set, and this is cost, right? Your cost is nothing but loss. So how many iterations are we talking about? 200, right? You can see this is 200, and this is the cost, right? We have to drop the cost over the iteration, right? So 10,000, so toward this is the zeroth cross, right? So now you can see that which is Adam. This one is Adam. The last line is Adam. Right? You can clearly see. So we are comparing against Adam, Ada Delta, SGD, Nestrov. This is what we're talking about. In fact, we spoke about all of them. Right? Right? And then clearly Adam is a winner. Right? So these are the kind of things that are published. Now CIFAR10 is also a image database. Right here you can see this Adam plus dropout Adam. Right? This line is Adam plus dropout, and the last one is Adam. In fact, Adam has become so good that you don't need to even do dropout, is what has been told here, right? So convergence is faster, better, both, right? So the same on CIFAR convent, you can see that, right? This is CIFAR convent first three epochs, right? These are the things, and these are the things. Now you can actually read the paper, right? So you see this line, CIFAR10, C. Can you tell me? Anyone can tell? Can you tell? Can you see what has been written here? Okay, let me just highlight this. Can you tell me what is the architecture of the neural network here? CIFAR10 is also. Can you tell me what is the architecture of the neural network? What is the first layer? How many neurons the first hidden layer has? Correct. So it's a 64 first layer. How many hidden layers? We have three layers. First one is 64, second one is 64, third one is, there are two hidden layers of 664. C64. C is nothing but a convolutional style neural network, and we will go through that. Okay, so again a special breed of neural networks, or the network itself. So we have a 64 neurons, and then 128, and then 1000 is the output, because CIFAR10 is also a 1000 class dataset. Okay, it's almost like ImageNet. ImageNet also is 1000, right? So CIFAR10 is also an image classification. So you can read all these things. What I'm trying to say is that go and read these original papers. It will give you immense, joy to see that so much work has been done. Okay. So this kind of things tells you that go with Adam. So this is image, large image, large image. I'm just trying to find out if they have done something in. You can even go there and see that there are two beta 1 and beta 2 for Adam, right? They have actually gone ahead and estimated for 10 epochs, for 100 epochs, what is the value generally, what it is. Okay. Okay. So let's do one thing. Let us go to the lab and just try to see how do we want to change our optimizer. Okay. If you remember, this is what we did. Okay. Let me just run it. Am I running it? Is this run? Let me just run it. I don't know what does that mean. Okay, let me print it. So what I wanted to show you is that let me just do this thing. Okay, and num class is not defined. Where is num class? Num class is defined. Achha, okay. So now num class is done. Okay, now I'll build the model. So if I do a compile, so now instead of RMS prof, what will I do? TensorFlow. How do I do this? So basically, I can do TensorFlow. So let me see. So let me actually implement Adam, right? And let's go to my Adam implementer. So let's see this thing. So I can actually do Adam and learning rate of 0, right? It is as simple as that, right? So I can just compile this, right? Sorry, something has happened to my keyboard. So Adam is not defined, which means I have to rerun this import statement once, and I've got my import statement done. I'll come here. Let me rebuild my model once more. Okay, and let me compile this, right? And sorry, this is what I was actually telling you guys. So let me just remove this and run this. So you can see my now model is compiled using Adam. Right? So code is this. Code is one line. All you have to pass is the, is the is your hyperparameters in this case, isn't it? But that's about it. The intuition is something that it is good if you are aware of the intuition. Okay. What we can do is, now that we have spent quite a bit of time on you know on this, we can finish batch normalization. It will not take more time, and actually batch normalization is also important. Which regularization? I have not. Oh no, I was actually so. No, no, no. It never gave any error. So I was showing you guys that instead of. So I was showing you, right, in the start of the class, that instead of adding dropout here, I could have added as a class here. Question was that why is it not at the compile time? Why things are in the layer? So that's what I was showing you, regularizer, right? You should not get any regularizer error. Where did you get the regularizer error? If you have run this one correctly, then there's no error here. I'm just running it again in front of you. Before compile means? No, so you have regularizer means what? Dropout, right? Or L1, L2. What were you adding? Right? So if you added a dropout layer, this is how you are adding it. See, you can see this, right? And this is compiling perfectly fine, right? Right. Okay, you can share the code and let me know, and we can discuss the issues, right? If you share the code, we can try to debug it. That is not a problem. Okay, that is not a problem. So we have to see the code to understand where is going wrong and what type of error also we are getting. It's possible that you might be getting some sort of typo error. That's also is possible, right? So let's do one thing. What shall we do? Shall we finish batch normalization and then come, because our assisted practice is on batch norm. Okay, and the reason it is on batch norm is because I think it's an important thing that we have to understand. Shall we do batch norm today, or do you want to reserve it for? Let's do batch norm, all right? Let's finish batch norm. Come back to this, and I think that will be a good closure of this week. Okay. Okay, let's do batch norm, guys. So what is batch normalization? Batch normalization is also, this is an important idea. The idea is that we do pre-processing left, right, and center, isn't it? In machine learning, even in statistics also, what we used to do, the moment we used to get data as a part of your EDA, right? Exploratory data analysis, what will you do? You will normalize, you will standardize, there are two different things. You will normalize because you will scale it down, right? Or whatever it is, you might use tell me one of the scalars that you might have used in your statistics or your machine learning or as part of your EDA. One sort of normalization technique that you might have used, min max scalar, right? Perfect. A min max scalar, right? Perfect. That's a normalization technique, right? Its objective is to reduce the scale to within a range, isn't it? Right. What is the standardization technique? What is this formula called? Do you know? Do you remember? Standard scalar, and this is also called as something, right? That is correct. Perfect. Right. It's also called as z-score, right? So these two concepts are very clear to all of us. Why do we do normalization? Or why do we do normalization? It is better to scale down if you have a large range of data, right? And especially now that we understand so much of neural network, it's obviously needed, because large numbers, right, might cause a big problem. If your output of a layer is a large number because of some feature is large, right, then all these not even Adam, the Adagrad style things which uses a square of loss in its denominator might cause more problem, isn't it? Right? So they will become exponentially high, like extremely big. the numbers are unmanageable, right? And if your output of a hidden layer, if the numbers get really big, what will happen? For say, suppose whatever reason, your second layer, let's go back to our, I'm just opening, okay? This I will send it to you guys, don't worry. Okay, if I think this might help you guys in some way. So let me just open this, right? So remember this layer, this is our layer, right? Suppose, for whatever rhyme or reason, this is very, very high. These numbers are extremely high, maybe in millions, right? And this is in tens, right? So there's a problem, right? Can you appreciate the fact that where the problem might lie when you try to do when you try to apply, right? If your gradient is too small and too big, your gradient also has to be really large to impact the change in the weights, right? Right? This will directly impact some weights, right? Something will happen. So we have to be very cautious of what we want to do. The other thing that is noticed in, at least in statistics, that we are aware, is that every time someone gives us data, we will do normalization, we will do standardization in the hope of what? What do we want to hope? We want to hope that our our data should be something like this. What do we call this? We are hoping, right? Our hope is this, that it should be, some sort of normal distribution, at least tend to be normal distribution. We know for one thing that if your data is normalized, we can handle the data much better, isn't it? If the data is also a different name for that, if it is a unit Gaussian distribution, right? If your data is Gaussian, follows a Gaussian process, you are somewhat saved. It is possible that you will actually have a better mechanism to deal with things. Same process applies. The same idea is that if my input data as part of my EDA, that I can actually do some scaling and normalization and whatnot to try to see if this has some sort of Gaussian nature or not. Why can't I do the same thing or find out for at each output of my layer? This is my output of my layer. This is my output. This is my output, right? Why can't I do that? And one thing is very clear: if I have a Gaussian distribution or a normalized, sort of numbers which is coming out of this hidden layer function, then my weights will be good. I have my layers can actually go deep also, right? Because each of these numbers have some sort of sense. It's not like it's not like one is in million, one is in tens, one is in something else, right? So that was the idea behind it, and I think in 2015-ish, there was a paper on, and I was reading the paper again. This was a batch normalization paper that came out in 2015. Again, you can see people from Google, right? So this guy, Sergey Arfov is pretty famous guy. Even this guy also, Christian Sazeti, he just released a ML paper on how to do mathematical reasoning. Okay. So they are the like really legendary guys. So read this paper, it is so well written. What it says is that if your numbers are not, what it says is that if your numbers of an output, see, read this thing. Training neural network is complicated by the fact that distribution of each layer's input changes during training. That we agree, because every hidden layer's output depends on the function that we have seen. We cannot control that process, right? As the previous layers change. That is correct. This slows down the training by requiring lower running rates and careful parameterization. That we have gone through it. So this process is called as, there's a term to this process called as internal covariate shift. Okay, just a name. Okay, but it is good to know. So the batch normalization is a process. What it says is that if you add at each layer end, it will try to normalize the output of each layer, each hidden layer, in a way which is acceptable. It's like sort of make it, apply, make it ensure that it is distributed, it actually defeats this internal covariate shift. Essentially, they are Gaussian in somewhat Gaussian in nature. That is exactly what it is. I strongly suggest please read this um, you know batch normalization paper. It is very well written, and I'm 100% sure you guys will be able to understand this. Okay, there is no two way about it. That much I'm sure. Okay, and this is what it says, right? Towards reducing, how do we reduce this internal covariate shift, right? So how do we reduce this internal covariate shift, right? So this is exactly what happens inside a network also, right? That you have two data points, like two extreme, and there's some which are huddling together. Instead of that, if you can, this we understand as part of data processing. This is what we continue to do, right? This is where batch normalization again as a layer form comes. What happens is that you can add this layer in your neural network architecture, and it will react per epoch per batch, right? So weight of neural networks gets updated during each training period, each epoch, that we understand, right? If the weights become suddenly large or less, right, it will cascade also all the layers. So hence normalization before the network is important. So you can normalize the data, but what happens, what about each of those layers? So that is where batch normalization comes, where you can add a layer, okay, like this, and then output of this will be normalized and ensures that you have a very good output for each of those layers. Okay, so that is what the crux of it. It's a very simple thing. It basically, what it does, it exactly does the z-score style thing. Mean, that each data point is divided, subtracted from the mean of that data point divided by my standard deviation. This is my standard deviation, right? Or root over variance, whatever. This is plain statistics. That is what this batch normalization does, right? It's exactly, and the other trick that it does is that, so it adds these parameters called as, it normalizes the output from active function activation before passing it, right? And so what it does is that it does this M, G, and B, right? We have these three parameters, right? And it expects the machine or the network to learn this, all the trainable values. That is also the other trick that it does, is that it expects the machine to learn all these values rather than hard coding it. So that's a nice trick that they have done to ensure that nothing is hard coded. All you just have to add the batch normalization step, and whatever, this M is the mean, okay. G is an arbitrary parameter to normalize the input, okay, to multiply the value between 0 and 1, and B is nothing but a bias that is added, okay, so that, the one more term is added as an output of the multiplication, okay. So all these parameters are learned in such a way that it ensures that, that numbers are between, so and this has changed big time, and this has helped, this alone has helped lot of, computer vision projects, right? Big time actually, okay, at that time. And if I'm not wrong, let me go to the paper one more time, okay. And if you remember, right, AlexNet has won the CIFA, the challenge, right? AlexNet has won the ImageNet challenge. These guys in this particular year, by just adding this batch norm, has increased, if I'm not wrong, I'm just trying to find out. So they must have written it somewhere, right? What they have found out is that, ImageNet. Anyways, I thought that this is the, by just adding this layer itself, they are right. Using an ensemble of batch normalized network, we improve upon the best published result on ImageNet classification, and they have breached that 4.9% mark, even exceeding the accuracy of human rates. So this one layer, very simple layer, has ensured that, your network has good values of the hidden layers, and it normalizes it. It reduces the time by 14% or 14 times or something like that. Okay, that is at its heart. Okay, sorry. Okay, so how do you implement? This is how you'll implement. Let's just go to the code. Okay, guys. So what I'll suggest, expect is that please, refresh your practice lab once more, please. Let me also do that. I think this is fine. And please go to self-learning, this 5.4. Okay. Let's go to 5.4. If you have already, just give me a shout out if you are done so that we can start. Okay. Any questions in batch normalization? There are, any question on batch normalization, on the concept of batch normalization? Very important concept, very interesting. People say that you can also use this as a regularizer. It has some sort of regularizing effect, but if someone asks you that this is a part of regularization, it is not actually. Okay, but it has a way of impacting, or basically allowing the model to generalize. In many times, many places, you will see that batch normalization as part of regularizer as well. Okay, but that's an after effect. They did not intended to do that, but it was such an interesting thing that it happened. So are we there in the practice lab? Please confirm. Guys, are we there in the class practice lab? Or is there, do you want this via like a demo, or do you want to run this thing? Okay, you are there in the practice lab, right? Okay, okay, okay. Can you load this thing? Load the assisted one and run the first line. Okay, I just wanted to. So if you run the first line, it's just a bunch of imports, nothing else. What we will use is that we will use this dataset called as make circles. Okay, and I was make circle is, you might not have this piece of code. I've got this piece of code. I copied this piece of code from sklearn. I wanted to see what is my data. I wanted to visualize my data essentially, and you can also copy this code from, just search sklearn and you can see this code. This is the code that I just copied from sklearn. Okay, because I wanted to visualize the code. Okay, so let me just make circles. Okay, and essentially it just randomly creates a data set which is circular in nature. You can realize, right? Can you put a linear regression in this particular data set? Is it possible? Do you think you can actually apply logistic regression to classify between yellow and non-yellow points? It will be difficult, right? Right. Let's do one thing. I know it's a hard week, guys. Don't worry. We are almost done. I think. Yeah, I think these are. I think this is mostly theory, but today is all about theory. But let's do one thing. Let's conclude this in a way that everything is there, and you have this weekends to actually brush over it, so that you can understand these things very well. So can you use SVM for this? You can use SVM. What happens if this number of train examples goes to 5 million, 50 million? What will happen? SVM has a very classical problem, right? There's an issue, right, with that max margin, at MMC, right? Even RBF also, right? The radial basis function, which exposes the features at a higher dimension, it might be difficult, right? But this is a very classical problem, right? The data looks like this, very difficult. Now let's define our model. What are we doing here? What are we doing here? We are just building sequential. We've added a dense network, a fully connected layer of 50 neuron, right? Are you so only this part is what I added, okay? I just copied this part. Are you referring to this part? Everything else should be same, okay? Everything else should be same. Only this is the part that I've added just before the class, guys. Might be because I wanted to visualize the code. If you want, you can also do this, okay? Everything else is, can you see the other things? Is it make circles there? The second line is this. Can you confirm that at least? Shiv Shankar, can you confirm that in your second line you have this? Okay, let us know. Okay, fair enough. So let's define our model. So we'll build sequential. We will do, it's a two-layer network. Okay, uh, can you use the, okay? So I'm not sure about, so I strongly suggest that maybe you have, so this is something that is there with me, and that is what has been provided to me. Have you got the email? And I have actually, already emailed this, whatever has been provided to me, okay? Maybe you should download that and start using that as well. Not yesterday, today morning before that is different, right? That was yesterday's. Today is lesson 5. So lesson 5, you must have already got it. So can you go to 5.4 and download this? Have you downloaded the 5.4 solution? This is the solution we are talking about, right? Yeah. Let's proceed, guys. So model is, let's do sequential, and then from model we are adding dense network 50. Again, there is a two dimension. Activation is ReLU. Are you seeing this? This is called as a kernel initializer. Let's actually open the the documentation of dense network. Okay. So not Keras. Let's open TensorFlow itself. In fact, we could have used, okay, dense. This is the dense layer. Yeah, names are confused. Yes, that's correct. Yeah, everything has assisted one, assisted two, like that. Yeah, correct. So now if you see the dense layers API, you will see the default kernel initializer is a Godot uniform initializer. Okay, and while we spoke a lot about optimizer, you also have to remember one thing: where do you start is a big problem, right? Where do you start your weight in that? How do you start? The starting point of a weight is also a point of active research, isn't it? There has been efforts, and I think people have realized that there are multiple algorithms, Javier's initialization, Hayes initialization, okay, are all there. And in this case, instead of the the default one, we are using Hay uniform. Okay, Hay is a person's name. It's not he is Hay. He's the one who invented the algorithm. Okay. So what we are doing here is that it's a simple two line network. Okay, our activation function in this case is that sigmoid. We will use a SGD. In this case, you can see, right, this is a SGD with mini batch by default, I guess, and the learning rate is 0.0.1, and we are doing a momentum of 0.9. Okay, if you want to use momentum, start with 0.9 value. Okay, so that is the accepted. That is anyway the accepted rate. Right. So what you have to do is, like, we solved this problem yesterday, remember? You have to do TensorFlow dot keras. Show your import statement. Can you see my import statement? You have to do TensorFlow dot. Yesterday we solved this thing in the other notebook as well, if you remember, right? Use the same thing. TensorFlow dot. Okay. Add TensorFlow dot keras in all of your imports. Okay. And that should solve it. Right? Okay. So and this is a, you can also do that. Yeah. Ideally, in production system, you just import TensorFlow as TF, and then as a verbose, you can do that, right? So that is what you should do it. So in this case, just since we are in the game of teaching, right? In the realm of teaching, it is sometimes easier to explain. But we will not write like this TensorFlow dot, again and again. Even this also makes you like I was using, right, like this. This is in a keras dot utils dot np. No, we will not write something like this, right? We will add our loss. We added our SGD, which is fine. Let's compile the model. So we have compiled the model also. In fact, if you let's see the model dot summary once, right? Shall we? That's wrong, right? It's TensorFlow dot keras dot optimizer. Can you look at this? Let me just put it here. I put it here. You can copy it, okay? Please copy the thing that I've put in the chat box. Okay. So if you do model dot summary, so you can see fairly. Sorry, folks. Yeah. Just one second. Okay. Sorry, I was sneezing. And you can see the model dot summary. It gives you two layers. Fairly simple. Okay. Let's do model dot fit. Our objective is to try to find out. Okay. Okay. What is happening? So is it running? Is it running? It's running. It's running. Okay. It's running. Okay. Okay. Let's do evaluate of model, right? And so you can see an accuracy, and if you actually plot a history, right, we can actually compute, we can compare between validation and accuracy, right? So we have reached somewhere, right? Now all we will do is now we will actually try to see whether how do we add batch normalization. We'll this is not needed, this is already there. Let me just add this via, all I will do is I will copy this TensorFlow dot, and if there is an error, I always welcome error because it just gives me an opportunity to fix things. That's it. I don't need all these things because I already have it, right? I don't need this also, so I will just copy it, right? And I will again generate some circles. Okay, generate my thing. Now in this case, as you can see, right, what I've done is that after my first dense layer, right, I have added a normalization, right? That's all I have to do. And if you actually check the normalization, batch normalization class, let's open the batch normalization class and see how it is. So fairly okay. Yeah, it's a deprecation, it's a warning, it's fine. Yeah. So batch normalization has, you can see it has 0.99 momentum, you have an epsilon and bunch of parameters, but I think that there's two parameters, right? Two things that we need. This is by default, it is fine, right? Now there's also an issue there's also a thing that you should know, and this is a very important thing that came up. Okay, so batch normalization, what it is doing, let us go back to the this is something that you should be aware of. This act of generating and normalizing happens in the data set per mini batch level, isn't it? Per batch level, right? You are training per batch, hence your layer will also get a batch value. If you have a 1,000 layer network and your 1,000 data point, you are passing 40 at a time. So your batch normalization will only work for the 40 records at a time, isn't it? Now that might create an issue. What is the issue? Your mean and your standard deviation is only for that 40. Remember that, right? You understand what you're trying to appreciate the problem that is happening? Generally, what we used to do earlier, we will compute the mean for the whole data set. In this case, we are only computing the mean and standard deviation for the batch and apply it only for the batch, right? This causes this has a problem not while training but while you are inferencing, as is stated in this particular API documentation. While you are doing a dot predict, you somehow have to note those things, right? So that is the way that has been noted is by again a moving average of the mean, while inference, the layer or the model preserves that moving average and applies at the inference time. Okay, this is an important understanding, also, and that one has to have for batch normalization, because since you're computing the mean and standard deviation per batch, you have to do something different, as in, like, not you, the model takes care of everything. Something different is happening. We don't have to worry about it. Not a single line of extra code that we have to write. It is just done for us by Keras, but inference has to be considered for that. All we did is that simply added this and nothing else. One line of code. Our life is done. If you actually do a fit, it's running. It's actually verbose is 0. If we do the verbose 1, I think it will be good, right? Let's do verbose 1. Okay, verbose 1 is good. If you do this, right, it will compute hundreds of accuracy. Let it compute. We are not afraid of logs, and you will see that there will be generally higher accuracy. Okay, and if you see this, right, 83 to, I don't know whether it has improved or not. Let's see. Did it improve? I think it's almost same, right? Because the data set is very small. It's anyway a toy data set. We wanted to show you that how to add normalization per layer, right? And that is what batch normalization is. It's a very, very important layer. If you want, please add batch normalization at every, generally at every layer. Not every layer, but at least in hidden, some of the in the early phases of hidden layers, you must add, right? Definitely, one should add. Are we able to run this assisted 1.ipynb? Fairly easy. If you are stuck, please let me know. Are you stuck? Is anyone stuck anywhere? LR argument is deprecated. Use learning underscore rate. Okay. So that is an SGDs. So what you can do is, like, wherever you are using this opt equals to SGD, this is a good thing, right? The deprecated means it is not used right now. So you can just change the LR to learning underscore rate. Okay. Satish, are you able to proceed, and are you able to fit the model? How much accuracy have you got? You've all got the same accuracy, 0.83 ish. Can anyone report the accuracy that you got after doing batch normalization? Okay. So seems like, I think we are okay with whatever we have done till now, right? Since there is no response, I assume that things are all fine. Your Jupyter Lab notebook is running exactly fine, and we are okay, right? What we'll do is, like, we will pause for today and for this week, and we'll regroup. 83.4, perfect. Same dot. Mine is a little bit higher, 0.838. 83.8. Okay, at least I'm talking about. You're talking about train. Okay, fine. This is fine. Good, very good. So now yours is a you have a running sample, right? And that this is the beauty of Keras, right? Things are extremely simple. And underneath, we have a lot of things that is happening. I also wanted to show you this. I was talking about, remember, I was talking about the graph, right? The object graph, sorry, the computational graph. This is what a graph actually looks like in a TensorFlow, okay? And this is what exposed in the tensor board also. Essentially, each of these node is a function, and these things are nothing but operations, okay? When we do compile, right, this thing gets created. This whole graph is getting created, and each of these has are under that gradient tape. The gradient tape is that automatic differential engine in TensorFlow. So everything is differential. So you can easily do backpropagation on that, right? Very interesting article. If you actually do this, go to TensorFlow, go to intro to alls, and it will give you an idea how such thing is done, okay, from a computational standpoint. Okay, guys, I think we have reached to an end of our, class. What we did is that we've extensively looked into um, each of the optimizer functions in a way that it is we have understood them logic wise, right? And we have also covered batch normalization, right? We have spent quite a bit of time today at the start of the session to go over a little bit of quiz so that we refresh our memory. What we will do when we regroup on next week is that we will discuss this classical problem in neural network called as vanishing gradient and exploding gradient. And while we do vanishing gradient, we will discuss, if you remember, the importance of choosing the right activation function. And we will discuss at that time that why sigmoid, why tanh, why ReLU, why not ReLU, and so on and so forth. Okay, these are things that we can discuss while we talk about vanishing gradient and an exploding gradient. Okay, this is a very classic problem in neural network. When you start coding all these things, you have to know. Okay, after that, what we'll do is like we will go to a very important topic, which is nothing but absolutely, yeah. Yeah. So it's like onion, right? We need to spend layers, right? The more you dig deep, the more you'll get. So what you have got for each of these optimizer is just an intuition. Mathematics of it, you also have to understand that each of these are also differentiable functions, right? Every time you add a layer, think about it, we just added a layer, right? And we said that there is some equation of batch normalization, right? In fact, if you let's go to the paper itself, right? The paper says this is the equation of batch normalization. Sorry, yeah, this one, okay. Might look a little complicated, but it is actually not. However, you have to ensure that the moment you add a layer like this, when the back propagation happens, the equation that you have written here must be differentiable, isn't it? Let's do one thing. Let's do model.summary to see one thing. Can you see the batch normalization has 200 learned parameters, right? The dropout has 0 parameters. However, this one has 200 learned parameters. Definitely, there are, it will come in waves and layers, but you have got good grasp of whys and whats. You can dig deep now, and we can all dig deep if you want. Each of them is a deep topic on its own, to some extent, but we can dig deep. You have the tools to now dig deep for sure. Okay. And on lesson 5, we will continue with the lesson 5 on Monday. We will look at hyperparameter tuning, isn't it? It's a very important problem. As with classical machine learning, we need to hyperparameter tune them, and there are so many parameters. There's actually not a lot of parameters, but we still have to know hyperparameter. It's a difficult proposition to do it in neural network, but we will see that in Keras we have something called as Keras tuner, and while there are other things also, but Keras tuner can help us achieve it. There are multiple methods, including a method of machine learning and a reinforcement learning technique to find out best hyperparameter. Okay, that is where we will probably end lesson 5. I think we will spend quite a bit of time on the hyperparameterization of things. After that, we will go to this idea of interpretability, or called as XAI, explainability. How do you explain an AI model? And that is what will give us a good basis of a neural network. Okay, so this is what we've left with lesson 5, and I would assume that we will close the day for close for this week and the day. And happy weekend, folks. If you guys have any questions, this is the time for asking the questions, or else we will start again from Monday. We will do that. Yeah, I will send Asha my notes today. So I only have one notes. I For the first and second lesson, I don't have anything else. I have not made anything on the first and second. Did I create anything? I don't think I have created anything on the first and second. Any Excalibur. Okay. Share the codes. You already have the codes, right? The code. There is only one extra code that I have done, which I have already given yesterday. The MNIST. There is an handwritten MNIST babysitting code. Okay, which was I have shared on second day. So yesterday I think they shared, right? So that you already have, and everything else is there in LMS. I have not added any extra code today. No, this I have already shared. Asha, can you actually answer? I have all before our session started, I have already shared it. Okay. Yeah, maybe it will come later. Yeah. But I will definitely share the today's notes on that optimizer. I feel that it has given me. I think it should give you help as well. Okay. Do we have anything else to discuss, folks? Or else let's call it a day. Okay. Thanks a lot. Happy weekend. Have a good one, guys, and let's regroup on Monday. Thanks a lot. Appreciate it.